Here's problem 25.4. A particle, mass 6.7 times 10 to the minus 27 kilograms, a charge of 3.2 times 10 to the minus 19 microcoulombs, moves along the positive axis with a speed of 4.8 times 10 to the 5 meters per second. It enters a region of uniform electric field parallel to its motion and comes to rest after moving 2 meters in the field. What is the magnitude of the electric field? Well, first of all, we need to correct this charge because it could not be microcoulombs. The smallest unit of charge that we deal with is 1.6 times 10 to the minus 19 coulombs, which is twice this value of charge. So we couldn't possibly have 3.2 times 10 to the minus 19 microcoulombs. So the micro is a typo. Let's take a look at what we got here. We have a charge and a mass. Let's imagine this charge of 3.2 times 10 to the minus 19 coulombs, and it's got a mass of 6.7 times 10 to the minus 27 kilograms. And it's going to move from point A to point B. We also know that this distance is 2 meters. We know that it has a speed of 4.8 times 10 to the 5 meters per second when it's at point A. So the velocity at A is 4.8 times 10 to the 5 meters per second. And it comes to rest, so the velocity at B is going to be 0, which means that the kinetic energy at B will also be 0. Let's calculate the kinetic energy at A. Kinetic energy at A is going to be 1/2 the mass times the velocity squared, 1/2 times 6.7 times 10 to the minus 27 times 4.8 times 10 to the 5 squared, and that gives us 6.7. 7.72 times 10 to the minus 16 joules. 7.72 times 10 to the minus 16 joules. Alright, nice to know. Hence, our change in kinetic energy, which is our final kinetic energy minus our initial kinetic energy, our final, in this case being 0, is going to be a negative 7.72 times 10 to the minus 16 joules. Alright, well then our change in potential energy will be the negative of the change in kinetic energy, so that will be a positive 7.72 times 10 to the minus 16 joules. That in turn is equal to the charge times the change in potential, where the change in potential for a uniform or constant electric field is going to equal the negative E field times the distance for a constant field. So this is going to be equal to a negative charge field times distance. So the E field will be equal to the change in potential energy divided by a negative charge times distance. That's going to be 7.72 times 10 to the minus 16 joules over a negative 3.2 times 10 to the minus 19 times 2. So we are going to get what? By 3.2 a negative 1206 volts. I'm sorry, newtons per coulomb or volts per meter. Well, we just want the magnitude of the electric field. The negative is giving us a direction, but we just want the magnitude. So the magnitude of this electric field is going to be a value of 1206 volts per meter or newtons per coulomb. So that's our answer.